This is a collection of exercises involving arrays and, in particular, functions that work with arrays. And we'll notice that because of that strange property that arrays have, where when you pass them to a function, the function ends up with access to the original data, you'll notice there's a very characteristic protocol for working with arrays in C when we pass them into functions. There really aren't that many rules about how to write a function or what kinds of parameters to take elsewhere. We've seen all semester we've written functions that take ints and doubles and mixtures of ints and floats and doubles and pointers and things. But it turns out that when you have a function that takes arrays, it does tend to have a pretty regimented style used. And in this course, this year, we're going to use, the style's actually been updated a bit in the past few years, and we're going to try and use that. And the idea is, because the array that you're passing in is the original from the function that was calling it, it is important that the function not modify the array unless it's supposed to, but the function can modify the array if that makes sense. And we'll see an example of that in the last one of these exercises. But in the meantime, we have to begin by writing functions to do stuff that we've already learned how to do. So here's a function that prints out an array. And it has no return value because its job is just to take an array and then print it out. It doesn't need to generate any other result besides doing that. And the key thing in C is that, I guess we need to write the function signature, so it's called print array, and it's of type void. And the thing in C is that when you pass an array to a function, all the function really gets is information on where to find the beginning of an array. If you think about the way we would draw an array on a diagram, here's my array A. It's an array of type int. And then here's the array itself. And, for all we know, I've got this pointer to the beginning. There's the array, and it just sort of goes off into the distance. And if I hand you an array in C, if you're a function and I pass you an array, that's basically what you're getting. You have no knowledge of how big that array actually is. The size of an array is fundamentally part of its type. But when I provide the array to a function, I actually don't provide the size information directly. I have to provide that myself, independent of the array that I send in. And that means that the protocol for writing functions that take arrays in C is you have to have some way of telling the function how big the array is. And for the time being, we're going to generally use this convention, which is we will pass in the size of the array as one of the parameters to the function. So I pass in int n, and then as my second parameter, I say take an int array of size n. And the key thing here is that we want to encode the size of the array directly into the function signature like this. So it's obvious to people that look at this function signature that the value of n is meant to be the size of the array A. To allow this, you have to make sure n comes before a in the list, because if you use the value n here, the compiler needs to know what it is. That's why I'm putting n first. Now what's interesting is that, and I'll admit right off the bat actually, it turns out you don't actually have to do this. You are allowed to write empty brackets, but only in a function signature. And the idea is because all I'm actually providing to the function is just this pointer here, information on where the first element of the array is, there's no secret about that in the language. And so I could just say, here's the size, and then here's the array itself. And then expect you, the function, and me, the person reading the signature, to understand that this is meant to be the size of the array. So writing this is actually optional, but I think it's a really good idea because it makes the code a lot more self-explanatory. It's less important for me to explain what n is for if it's obvious to you that n is supposed to be the size of the array. Now, it turns out for 2D arrays, it isn't optional. For 2D arrays, you can't leave the brackets empty. And we will see later in the course why the empty brackets, why having that option is really important, because there are times where we can't easily tell you the size of the array. You have to figure it out through some other means. But the key thing is there is no general way, if I hand you an array, for you to always determine the size of that array. I have to give you the size some other way. And I think the obvious way for now is I just hand it to you in a variable. Okay, so inside the function, I can loop through the array and print it out the way I would in some of the previous examples. I'll create an int called I. I'll loop up to n minus 1, and then, At each step, I will print out the current element of the array, a sub I, and at the end, I will print out a new line. And that's, I think, all there is to it, because the function's not supposed to return anything. It's just supposed to print the array out element by element. All right, now I'm in a sticky situation here. I really should be testing this code before I keep going, but there is one more function that isn't, there's no signature for it yet, so the code won't compile until I write this one more function. So I'm going to We'll hope I don't get into any trouble doing this, but I will hold back on testing the print array function for a little bit longer. So this next exercise is, here's an array, it has n elements, return the largest element in the array. And of course, whenever you get a problem like this, no need to draw a full diagram, but you might actually want to map out, okay, here's some, like, make a few examples of arrays. Okay, there's 6, there's 10, 111, 17, 187. And your job is to figure out, of all of these elements, which one is the largest one, and then return that value. And it's worth considering, because we accept the size of the array as one of our arguments, that does open us up to the usual shenanigans of having an argument with an invalid value. And I'll get to that in a minute. I'm going to begin by writing this signature. So the name of the function is maximum element, and it takes its parameters, an integer n, and an integer array a of n elements. So the thing here is that what if somebody were to, for some reason, pass in -1 as the value for n? Now, in a lot of contexts, a function is not required to correctly deal with every possible input. It would be valid for the function specification as a precondition to specify this function assumes the value of n is always at least 0. If you provide a negative value, something undefined will happen. That's your fault for doing that. But it is good to at least be aware that that could happen here. So in this case, it says, look, there can't be a maximum element if the array has nothing in it, or if the size is negative, whatever that means. So if that's the case, return 0, just as a placeholder. So if n is less than or equal to 0, return 0. And you've already seen my affinity for asking midterm questions with conditions like this on them, so you should prepare yourself to handle special cases like this. Okay, so now if we get down here to line 40, the array has at least one element. And what we have to do, we obviously don't know what the largest element is until we've looked at all of the elements. We also don't know where in the array the largest element will be. So in this example here, the largest element is right at the end. But of course, there's no reason that that has to be the case in general. So for example, in this example, the largest element is in the middle. And what we want to do is look at every single element and keep track of the largest one that we've seen. And this is an interesting pivot in the course because we have to spend a lot of time, starting with arrays, thinking about the algorithm that we have to use. We've got all of this data. The array could have a million things in it. How do I ask a question about all of the pieces of data? And then what do I keep track of to be able to answer that question? So here's the way I'm going to handle this. I want the largest thing in the array. I'm going to look through the array from left to right. And as I go, I will learn more about the elements of the array. But let's just bear with me here. Let's suppose I haven't looked at anything yet. If I just look at the very first element and I ignore everything else, what is the largest thing I've seen so far? Well, obviously, if I only look at the first element, the largest thing I've seen is just the first element. So let's start with that. For lack of any better information, let's assume the first element is element number 0. Okay, and then down here, I'm going to return the maximum that I find. And so what I'm going to do now is I have, an initial hypothesis for my largest element. It's the thing at the beginning, just for lack of any better ideas. What I'm going to do now is I'm going to look at every other element of the array, starting at index 1, and I'm going to ask the question, is this element bigger than the element I already think is the maximum? Let's actually trace through this. Let's just sketch this out. So I'm going to start with the maximum. Let's draw it like a variable box. So I'll make a variable called max, and it's an int. I set it to 6 because that's the first element. I then take a look at 10 and I ask the question, is this bigger than my current maximum? The answer is yes. If the answer is yes, I replace my current maximum with the element I'm looking at. Then look at the next thing, is this bigger than my current maximum? Also yes, so I replace my current maximum with this. I ask again, is 17 bigger than 111? Nope, so I just keep going. Is 0 bigger than 111? Nope, so I just keep going. So I start with some initial idea, just something to start with, and then I walk through my other elements and I keep asking that question over and over again. This is a really good time to remind those of you watching, to remind everybody that when you get to a point when you have to solve a complex problem like this, writing code is often the last thing you want to do. Literally, there's no benefit to writing code until you know what you want the code to do. A lot of people, especially at this point in the course, their reaction to interpreting a problem is just to start writing. And that can work, but keep in mind that can also result in you sort of running away from yourself with just too much code and not really knowing what it's supposed to do. You've noticed already with things like midterm questions, a lot of midterm questions have a one-line answer. There's no reason why you should have to write the one-line answer, but often writing lots and lots of code is actually counterproductive. Until you know what you want the code to do, writing lots of code is just going to get in your way. So here, I know that I'm going to start with my first element as my best guess for the maximum, and then I'm going to walk through all of the remaining elements. So I start at index 1, which is the second element. I keep going up until the end, and I add 1 at each step. And then at each step, I ask this question. If the element I'm looking at, that's a sub I, is larger than the maximum that I currently have on file, then set my current maximum to be the current element, a sub I. So I've got an if statement inside of a loop here. So one key insight to observe is if you want to talk about all of the elements of an array, so if I ask for the maximum thing among everything in the array, when you get a problem like that, you pretty much need a loop. You need to look at each element yourself. You can't expect the language knows what you mean. There isn't any general way of handing over an array to the language and saying, go figure this out. If you have to make some judgment on every element of an array, you have to look at every element of an array. Now, I will observe that I've started my loop at index 1, because I've noticed that obviously I've already dealt with index 0 because it was my initial guess. To be honest though, I often, when I write a loop like this, I write 0 here. I waste a little bit of extra time. Like the computer takes one more step. It doesn't hurt anything because you might be able to satisfy yourself that this just does nothing on I equals 0. So there's nothing wrong with doing it that way. And there's no reason why doing it this slightly more technically correct way is actually of any help. Because even if you do put 0 here, the compiler might notice what's really going on and fix it for you. So just something to keep in mind. And then when I get down here, I return the maximum that I've computed. So I want to test those out. And before I test them, I'm going to show off the testing code that I have in main. But I also want to talk about these two other functions. So here's a function we'll write next in a few minutes called linear search. And the idea here is I want to look at the whole array and ask a question, but this is not going to be what's the largest element. Instead, I want to ask a question like, does the number 10 appear in this array? And if so, tell me where. Or I could ask, does the number 18 appear in this array? The answer in this case is no. Obviously, it could be the thing I'm looking for isn't found. And so this is a search question. Here's an array, go search the array for this element. So I give you an element to search for, and this is going to use an algorithm, a very simple algorithm called linear search, which is just, if you want to go search for something, look at everything one by one. So in linear order, starting at the beginning. That's the next thing we're going to do. After that, we're going to work on this problem. The reason this problem is interesting is that the result of this problem is an array. And it's an example of a function that doesn't return something. It actually modifies its input. It takes an array from you, shuffles the elements around, and the result is contained in the array that you handed over. So it's reversed the array. And you'll notice I've added this extra field here, this side effect. It doesn't have a return value. Instead, its effect is manifest in the original input that you handed over. But okay, let's take a look at the testing code. So here's some arrays, A1 and A2. So notice that A1 starts with 10 and ends with 111. A2 starts with 1 and ends with 11. Okay, so we'll start by testing print array. Then we will test maximum element. These tests down here will not do anything helpful at this point because we haven't written those functions yet. But we'll get there in a minute. So that warning is that's not innocuous. We should solve that problem, but we'll get there in a minute. All right, so contents of A1. So we're testing out print array. So here are the actual contents of A1, and then that's what it prints out. That looks good. It prints every single element. When you're verifying something like this, you should also try testing it on arrays of size 1, for example, and make sure that, of course, the first and last elements are preserved. Looks like A2 looks good. The largest element in A1 is 116. That looks good. The largest element in A2 is 19. I think that was a typo. Just fix that. All right. And obviously, this is the results of linear search. This is random garbage because the function doesn't have a return statement, and so its return value is undefined. And then down here, the reversal doesn't look like anything because we haven't written that function either. All right, so let's talk about linear search. So again, like I said earlier, it's probably not the best idea just to start writing with a question like this. You will end up, even if the code ends up working, you'll end up with too much code and it'll be pretty cumbersome. Instead, sketch yourself out an example of an array or maybe two arrays and decide how you're going to solve the problem. Decide what steps are taken, what do you do once, what do you do repeatedly. So here's the way this is supposed to work. you hand me a search element, something to look for, and you hand me an array. And you can see here, I give you the size, and then you get an array of that size. And the purpose of the function is go looking inside the array for this value. If you find it, tell me the first index where you found it. It says smallest index. And the idea, I'll draw a second example here. Okay, so let's search for the value 2 in this. So 3, 1, 2, 4, 2, 2. So the idea here is if I ask you to look for the element 2, well, it does actually appear in more than one place. The function is supposed to return where the element is found. And for the sake of making that deterministic, it says return the smallest index where you find it. And so in this case, it's this. Oh, it's actually at index 2. That's not very helpful. But it should return 2 here, not 4 or 5. It's specific. It wants the first occurrence if you go left to right. If the element you're looking for isn't in the array, so if let's say I go looking for the number 6 in that second array, then it returns -1. So the logic here is that linear search returns an index of the array if it finds what you're looking for. And because -1 is not a valid index, then if it returns -1, you know that the element wasn't found. So the way I'm going to do this is I'm going to start looking. I'm going to go from left to right, so index 0 up to index n-1, searching for the value that you gave me. If I never find it, so I loop over all the elements and I never find the thing I'm looking for, then we will return -1. Otherwise, as soon as I find the value, the function can just end. I just return that index and we're good. So int I equals 0, I is less than n, I plus plus. And let's see, at each step I want to ask, is the element I'm currently looking at, so that's a sub I, is that equal to search element? And if the answer is yes, well then we're done. If I go from left to right, 0 up to n, and I find any element that matches, I have found the first occurrence of that element. I just return the index I'm working with. All right, and then if I get down here, if the loop ends, well, that means I never hit this return statement. The loop went over every single element and none of them match the criteria. So if I'm down on line 72, then the element I was looking for must not be in there at all. So I return -1 down here. All right, let's try this out. All right, and that warning from earlier is gone. We'll run it. Okay, so there's this. We fixed that typo there. That's nice. And we begin searching. So search for the value 6 in A1. And you'll notice there's index 0. There's index 1. That's the value 6, so it returns 1. Search for the value 7 in A1. Well, the value 7 isn't in A1, so we get -1. Okay. Search for the value 6 in A2. So there's A2, and we can see it doesn't contain a 6. So the result is -1. Search for the value 7 in A2. Okay, well, there's index 0, index 1, index 2, index 3 contains a 7, and so we return 3. All right, so let's talk about reverse array. So this is a problem that can really confuse people. And the reason it confuses them is not necessarily that the problem doesn't make sense. It's that they get tongue-tied, for lack of a better term. There's a tendency to think, okay, so the purpose of this function is to take an array, and when the function's over, all of the elements of the array are still in it, but they're in the opposite order. So I can illustrate that. If I call reverse array on this thing here, the resulting array, when I'm done, should look like this. So it'll be 2, 2, 4, 2, 1, 3. In other words, this goes here, this goes here, this goes here, this goes here. We just flip the order of everything. So people look at this and they say, okay, the result has to be in the same storage that it was already in. So what they do is they begin thinking, oh, I guess I have to swap this element and this element, this element and this element, and that can get really confusing, and you write this big mess that may or may not work. There is another solution. Because you might have noticed, it wasn't so bad if I have two arrays. If I only have one array, I'm sort of fighting with myself to avoid accidentally overwriting some data. And you might want to try this. See if you can make it work with just one array. The key thing here is you were given an array, but you're always allowed to make another array. There's no requirement that you have to only use the array you were given. There have been questions where the question might say you may not create any extra arrays, but a question like this, generally, you can do whatever you want, including create an array. So here is the way I think I should do this. Let's clear this. You give me this array here. That should be fine. So there's 6, 10, 111, 17, 187. Here is the way I'm going to play this. I don't want to worry about things like swapping 187 and 6. That seems like it could be a bit messy. Instead, what I'm going to do is this. I want to avoid a case where I accidentally step on something that I'm going to need in a minute. So what I'm going to do to make sure I don't have that problem is I'm going to make, here's my array A, I'm going to make a copy of my original array for safekeeping. I make a copy in a separate array. Then I go through and I just ignore everything in A. I treat A like it's been cleared out. And then I just copy everything back, but I start at the end. So I take the last element of C and I copy it into the first element of A. I take the second to last element of C and I copy it into the second element of A, and so on. Because I'm using a second array, I don't have to worry that I might be overwriting values that I otherwise would need. And so I'm going to put that diagram on hold for a minute and come back to it when I get to the algorithm. The first thing I have to do, in my mind, is create a new array. So I make a new array of size n. Now I'm going to copy every element from A into C. Okay, so I'll need a loop for that. So index 0 up to n. And then I just, at each step, I say, okay, I want to take whatever is in A sub I and put that in C sub I. Just a one-for-one copy from one array to the other. And notice that if you want to copy an array, you have to write a loop. You are not allowed, you are absolutely never allowed to write this. This does not create a copy of an array. Because remember that when we refer to an array in C, we're actually referring to some strange pointer. So if you want to copy all the elements, you have to do it manually. And it turns out there actually is a library function that'll help you with it. But the library function, if you want, the library function though just uses a loop. There is no faster way than to just use a loop. Okay, so I copy every element from A into C. So now I've got a situation like this. And what I want to do now is I'm going to sort of pretend that A is empty. I mean, A contains elements, but who cares? We just pretend there's nothing in there. What I want to do now is I want to copy it so that everything ends up in the reverse order. This requires some thinking, and I'm not kidding about this. Maybe watch this video, take a couple of days, then try the problem from scratch. See if you can map it out on paper. Because on a midterm, when you get a question like this, it's not going to be trivial, and it's really easy to really mess things up if you don't think the logic through before you write code. Here's the way I want to do it. I want to start at the end of C, and I want to put that in the first element of A. And the way I like to think about this is I'm going to hold my place at A at each step, and I'm going to hold my place in C. And then, as I go, I'll begin at each step, I'll take something from where I am at C and put it in wherever I am in A, and then I'll move up. So in this case, I'm going to move to the next element of A, and I'm going to move to the previous element of C. So at each step, I'm keeping track of a position in A and a position in C. The position in A moves from left to right. The position in C moves from right to left. I guess I probably should draw in some indices here. Okay, so it sounds to me like I need two index variables. Is there a way of doing this problem with one? Absolutely. There is a way of using only one index variable for this. However, in my mind, it seems a lot easier to write if I use two, because what I've drawn out, my visualization seems to require two indices. So I'm going to call my variables A index, and I'm going to start my A index at 0, because I'm going to walk from left to right. So I'm going to change my diagram to look like the initial configuration again. So I'm going to start at the end of C and the beginning of A. So A index starts at 0, C index starts at n-1, the last valid index. And now what I'm going to do is I'm going to keep going as long as A index is less than n. I'm going to fill up every single index of A starting at 0, working my way up to n-1. So while A index is less than n, and at each step what do? Into the element of A, not I, into the element of A at my A index, I copy my element from C. Okay, so I pull something out of C at the index that I'm using in C, and I put it into A at the index I'm using in A. And then I have to make some progress. I have to have my incrementation. So at each step, the A index increases. I move to the next element of A, and the C index decreases. I move to the previous element of C. So I actually think I should trace through at least one iteration of this conceptually to make sure I have it right. So I start my A index at 0. My C index starts at 4. I ask the question, is A index less than, I guess n is 5. Is A index less than 5? Yes, it is. Okay, so keep going. Take the element C at C index, that's 187, and store it in A at A index. All right, A index gets incremented, so now it points here. C index gets decremented, so now it points there. And hopefully that's enough. Maybe we could trace through more iterations if you weren't convinced. That's enough to believe that it seems like we are doing what's expected, the first element's correct, and we're making progress. And we also would want to verify that when A index gets all the way to 5, that we stop, because the array, of course, doesn't have an index 5. And let's try running this. So the function has no return value. Instead, all of the modification is just stored into the original input array. Okay, so at the beginning, A1 was 10, 6, 17, 116, 11. And at the end, after I've reversed it, all of the elements are still there, but they are in reverse order. And we can see A2 similarly did get reversed. So this does work. And just at the end, I want to add another emphasis that this is not the only way of implementing this. There is a way of implementing this that uses one index variable and doesn't create a second array. And it might be interesting for you to try that out, but it's important for me to make sure you know that it doesn't make any difference which method you use. So therefore, try and use a method that makes sense. It's true I needed an extra array for this, and I needed 2 index variables, but I was able to map out what I was doing so that I could be confident that it would work. A lot of people try and write code that uses few variables or few arrays. The problem is, if that means you spend 2 more hours debugging it, or you get stuck and have to start again, it isn't saving any real time. So keep that in mind. There's no requirement that you come up with the solution with the fewest lines of code. It's also true that the solution that only involves one array and one index actually has a lot of special cases that are hard to find and test in some cases. So even if the code appears to work, it may not work in all cases if you use that approach. This, on the other hand, is, once I have it all mapped out, pretty foolproof. It doesn't seem like there are many cases where I need to worry too much. I suppose I might want to consider maybe if n is equal to 0 or something to make sure I don't do anything weird there. Although I think it would still work in that case. Because I have code that's a bit that's spread out a bit better, I don't have to worry as much about there being special cases hidden inside something that I haven't discovered yet.